Okay, enthalpy of solution. We are going to kind of answer the question, why don't all ionic compounds dissolve in water? Let's look at this. It's a little messy here. If you have KCl, that's a K and a chlorine there, potassium chloride, you throw that into water, it will dissolve up into K plus aqueous plus Cl minus aqueous. Yeah, no problem there. But you can kind of think of this dissolving as two steps. Step one, you have to separate the potassium from the chloride. Step two, you have to get the potassium and the chloride each surrounded by water molecules. So, if we have our KCl, that should be Cl there, goes to K plus plus Cl minus. The energy, it's going to take some energy to separate K plus in the gas stage from Cl minus in the gas stage, because if we're completely separating that KCl, then the two will be in the gas stage. And that takes a lot of, or the gas phase, that takes a lot of energy to break apart those two ions. The second step is surrounding them by water. This K plus in the gas stage plus chloride in the gas stage becomes K plus aqueous plus Cl minus aqueous. And when these two, note that a K plus is attracted to a Cl minus through this ionic interaction. However, when you throw water in there, that potassium is very strongly attracted to the negative oxygen atoms. Recall, water is very polar. These oxygens have a very decent partial negative charge to them. So you can replace the attraction of the K plus to the Cl minus with the attraction of the K plus attracted to, here are 4 waters, there's actually going to be 1 in front, 1 behind, to 6 negative oxygens. And the chloride will be attracted to the hydrogen end of the water molecules. The chloride will be attracted to 6 water molecules also. So you're replacing one, you can look at it as one ionic interaction with 6 of these ion dipole interactions. When we look at the energy diagram, if we look at this one right here, what we see is, here's our energy, here is our KCl solid. To break it up into the gas phase, we have to break through all that lattice energy. It takes a lot of energy you'd have to add to get to K plus gas plus Cl minus gas. However, when you start looking at the hydration, the enthalpy of hydration of forming these ion dipole interactions here, that loses a lot of energy. We get a lot more stability, such that K plus aqueous plus Cl minus aqueous, when we put in water, is lower in energy than just KCl solid. Note, when you actually do the process, if you have this KCl solid and you dissolve it in water, it does not turn into gaseous ions and do that. This is just an example of Hess's law to help us understand what's going on. The first thing that happens is they must separate from each other and then get surrounded by the water molecules. This is all happening simultaneously. Nothing's ever going into the gas phase. However, when you're looking at the energy of the system, recall with Hess's law, we can just add up the energies of various processes to get the overall energy. What we're trying to get is, okay, what's this energy value here? What is the energy of dissolving KCl solid into water? What is this energy gap? Well, you just take this energy and subtract this energy from it, and you get that gap through Hess's law. But note, this is a relatively small energy gap here between two very large energy values. This is a very large energy value to do this, and then you have to subtract off this very large energy value here. So this is a difference between two large energy values, gives us this small energy difference here, but note, it is more stable, it is energetically favorable to have the K plus and the Cl minus being aqueous when you throw water in here. And entropy also plays a role. It is also entropically favorable. It is more random to do this also. When you look at something like silver chloride, which we know does not dissolve in water, it's a slightly different diagram. If we have AgCl, and we try to say, okay, what's the gap between AgCl, the energy gap between AgCl solid that's mixed with water, and plus and Cl minus, both dissolved in water, what we find is you take this lattice energy here, and then you have to add the corresponding, take into account corresponding hydration. And what we find is this is not energetically favorable. The difference between this very large energy value and this very large energy value shows, this gap here is endothermic. It takes energy to do that, which means AgCl is not just going to dissolve in water because it's not energetically favorable. Now, yes, it is in terms of entropy favorable because this is more random. And so what we're going to find, and we're going to discuss it much further in a couple of chapters, a lot of times our delta H, our enthalpy, and our entropy kind of have to duke it out a little bit to see which one is going to win. And we're going to have a whole chapter on entropy versus enthalpy and whether a reaction is going to go or not. Okay. Continuing on. Let's look at other factors that affect the solubility. And we're going to start by looking at gases dissolved in liquids. And gases dissolved in liquids, good news, we've got some math that describes it. It's Henry's law, where S equals Kp, where S sub G is the solubility of the gas in the liquid. How soluble is the gas dissolved in the liquid? K is just a constant, and P is the partial pressure of the gas above the liquid. If you have a container that has oxygen gas above water, will any of that oxygen gas dissolve in the water? Well, it depends on the pressure of that oxygen gas. Note, this is a fairly simple equation. With that being a constant, if you increase the pressure of, say, oxygen gas above water, note that that means you will increase the solubility of the gas in the water. And this is what is seen. The higher the pressure of the gas, the more of it that will dissolve in the water. And you see this all the time with soda. You know, if you have a 2-liter bottle of Sprite or Pepsi or something like that, there is carbon dioxide gas dissolved in that soda. In the solvent in soda is water. And so you have the carbon dioxide gas dissolved in there, but you note in the soda bottles there's always a little bit of space above the level of the liquid in the bottle. And so as soon as you open that bottle for the first time, it turns out that space was occupied not by air but by carbon dioxide. There's a certain pressure of carbon dioxide above the liquid of the soda. When you release that cap, you let that pressure go. Some of that carbon dioxide pressure gets released. And so if the pressure goes down, you release some of that pressure by opening that soda bottle, the pressure goes down. That means the solubility of the carbon dioxide in the water goes down, and then you get the bubbles forming in the liquid. The bubbles, carbon dioxide gas start forming when you release that pressure. Okay. But we must also look at this in terms of Le Chatelier's principle, because it turns out a gas plus a liquid solvent gives you the saturated solution of the gas completely dissolved in that solvent, plus energy. It turns out dissolving a gas in a liquid solvent releases energy. It's an exothermic reaction. And one way to look at this, we'll discuss this a lot more in the equilibrium chapter, but one way to look at this using Le Chatelier's principle is that a gas plus a liquid solvent will be in equilibrium with a saturated solution plus energy in the form of heat. This brings us to Le Chatelier's principle, which will be very important coming up in 2 chapters when we discuss equilibrium. Le Chatelier's principle is simply this. When you have a chemical reaction, any factor that affects the equilibrium will cause that chemical reaction to try to counteract that factor. When you look at Le Chatelier's principle, he normally calls it a stress. If you put a stress on an equilibrium process, the reaction will adjust to relieve that stress. So what Le Chatelier is saying is, if we look back here, if you have a gas plus a liquid solvent, it gives you a saturated solution plus energy in the form of heat. If you increase the temperature, you just raise the temperature of this situation, then you've got too much heat. If you artificially raise the temperature, you are adding heat to this reaction. And heat is a product. You've put a stress on this process by adding too much product, too much heat. Le Chatelier's principle says then the equilibrium will shift to try to solve that problem of too much energy. The equilibrium will shift back the other way. The gas will try to come out of the liquid because you added too much energy. Energy is a product of this process. If you add more product, the equilibrium will shift back to form more reactant. And you know this also with that soda, because carbon dioxide gas dissolved in your liquid soda gives you saturated carbon dioxide in your soda plus heat. It took heat to do that. What happens if you warm up a glass of soda? What happens when you warm up your soda? Yeah, it loses all its fizz, because when you warm it up, you add energy, and so more gas is going to come out of that liquid soda when you heat it up. And so that's how temperature affects the solubility of gases in liquids. The higher the temperature of the liquid, the less gas that will dissolve in that liquid. Okay. And yeah, there it is. Here it is shown right here. There we go. Yeah, you add heat, increase the temperature. Too much heat is in the product. The reaction shifts to the left, the other way, to get rid of that heat. Increasing temperature decreases the solubility of a gas in a liquid. All right. Now, if you have a solid dissolved in a liquid, it is also affected by temperature, but it's not a real good predictable pattern. All right. Let's say in general, just in general, often increasing the temperature increases the solubility. This is commonly seen with sugar in water. You can dissolve sugar a lot better, and you can dissolve a lot more sugar in hot water than you can in cold water. Sweetened iced tea doesn't hold that much sugar, but if you heat up that tea, make hot tea, that will hold a lot more sugar. Hot water holds more sugar than cold water, and this is fairly common. We often see that increasing the temperature increases the solubility, but not always. Here's a little chart over here. This diagonal line here, we have solubility on this axis and temperature on this axis. So increasing the temperature increases the solubility. So whatever this thing is here, increasing temperature increases the solubility of the thing, such as sugar and water. If you have something like salt, sodium chloride, and water, it turns out sodium chloride just dissolves in water the same amount. Its line is something like this. Sodium chloride dissolves in water really, really well. Increasing the temperature really does not increase the solubility of sodium chloride in water. Note also there are some things that don't dissolve in water, and so increasing the temperature might not get it to dissolve in water at all. Silver chloride, doesn't matter what temperature you raise it to, silver chloride just has a very, very low solubility in water. And your book has an interesting chart on there with a whole bunch of compounds. Looks like all sorts of different curves that show you, yeah, this whole relationship between temperature and solubility of solids dissolved in liquids is kind of chaotic. Often increasing temperature increases solubility, but there's all sorts of variations in there. All right. And this can be used if you go on to organic chemistry. We use this all the time to recrystallize a product. This will purify it by taking a solid and dissolving it in the solvent when it's very, very hot, making a saturated solution of our solute dissolved in the very, very hot solvent. There, the temperature is hot, therefore the solubility is increased. Then we cool down that mixture As we cool it down, we lower the temperature, which means lower the solubility. It was already saturated, so some of this or most of that solid recrystallizes out, becomes a solid again, because as we decrease the temperature, we decrease the solubility of that solid in that liquid solvent. And it turns out when you do this process, it tends to purify that solid. All right, that's enough for this video. We're going to go back now in the next video and look at the units of solubility. You're familiar with one, probably molarity, moles per liter. Let's review that, and let's go looking at some other measures of solubility and of concentration.